All right, kids, thanks for joining me in my tutorial on Le Chatelier's principle, which deals with changes in equilibrium. So the first thing we'll do is discuss this Le Chatelier principle business, and then the second thing that we'll talk about are conditions that would lead to changes or shifts in chemical equilibrium. So let's recall what chemical equilibrium actually is. So if we have a system here of a reversible reaction, so our reactants are becoming our products, and at the same time our products are turning into our reactants. Its equilibrium is when the forward reaction, so the reactants becoming the products, is happening as fast as or at the same rate as the products turning back into our reactants. So that would mean that we would get no change in our reactant or product concentrations when the system is at equilibrium. So what is Le Chatelier's principle? Well, first of all, this is Henri Le Chatelier, and as you can tell, I love him. And Henri Le Chatelier studied changes in systems and their equilibrium and wondered what would happen to the equilibrium if you changed certain conditions of that system. And so he came up with this principle that we call Le Chatelier's principle that states that if the conditions of a system that has reached equilibrium are changed, then the system will react to counteract those changes. So the short and skinny is that if you have a system that's reached equilibrium and you mess with it, it's going to react by trying to get back to equilibrium. So what were these conditions that Le Chatelier spoke of? Well, the first condition are changes in concentration of the reactants or the products. The second condition are changes in temperature of the system. And the third condition is pressure or volume, because they're related, of the system. So I'm going to go through each one of these and talk about how changes to these things will affect the position of equilibrium. And I want you to remember that a system at equilibrium is a lot like two things on a seesaw or a teeter-totter. The reactants and the products are balanced in a way that the forward and reverse reaction are equal to each other at equilibrium. And if you do something to upset that balance, so to put it off kilter, then that reaction is going to do something to try to right itself again and get back to equilibrium. All right, let's talk about what would happen if we change the concentrations of any of our reactants or products. So we're going to use this hypothetical reaction, A plus B yields C plus D. And you just need to remember that everything on the left we're going to refer to as reactants, and everything on the right we're going to refer to as products. And something else you need to remember, because we're talking about changes in concentration, remember that anything that's a solid or a liquid doesn't have a concentration. We don't put it into the equilibrium expression. Therefore, changes in anything that are pure solids or pure liquids aren't going to have any effect on the equilibrium of the system. So let's do an example. Let's say that we wanted to increase the concentration of A. So we're adding some A to our system. How is that going to affect our system, or how's the system going to respond to that? The system would respond by trying to get rid of that added A. And so the only way it's going to be able to do that is to use it up. And the only equation that uses A is the forward reaction. So the forward reaction would actually speed up and use up that extra A. So what we call that, or how we phrase that, is we say that the reaction is going to shift to the right. So equilibrium is going to shift to the right. What that means is, of course, the forward reaction speeds up. So if it's shifting to the right, what's going to happen to our concentrations of all the other things in our system? Well, you would find that the concentration of B is going to decrease because it's being combined with A to form C and D. And your concentrations of C and D, of course, would increase. All right, let's do another example. So what if we removed something instead of adding something? So what if we removed B? So we took some of B away. What's that going to do, or how is the system going to respond to that change? Well, what the system's going to want to do is it's going to want to try to replace what's missing. So if B gets taken away, or if we take lower its concentration, then the reverse reaction would speed up. C and D would combine faster to replace the B that we just removed. So by removing the reactant, B, the reaction is going to shift to the left. That's what we say. We say it shifts to the left. And of course, assuming that the other things are not pure solids or liquids, their concentrations would also change. So A would increase because the reverse reaction speeds up to produce more B, but in the process will produce more A as well. The concentration of C will decrease, and so will the concentration of D, because they're being used up to replace B. All right, and let's do one more quick example. You'll notice this time I gave you states of matter for this reaction. So A is a solid, B is a gas, C is a solid, and D is a gas. And so what would happen if we were to add more A? Now, if you remember correctly, we don't put pure solids into our equilibrium because their concentrations don't change. You can't change the concentration of a solid, because if you were to actually remove or add to a solid, all it is just the same substance, and so its concentration wouldn't go up or down because you can't measure a solid in moles per liter because it's just all one thing. So if you were to add more A to the system, you would find that nothing would happen. And that's because A is a solid, and adding a solid doesn't change the equilibrium of this system. All right, so to summarize changes in concentration, if you were to increase the concentration of either a reactant or a product, the system's going to try to remove that added amount, and it'll do that by speeding up the reaction that uses that substance. If you decrease the concentration of a reactant or a product, the system's going to react by trying to replace what you took away, and so the reaction that makes that substance will speed up. All right, so the second thing that, or second condition that you can change about a reaction that has reached equilibrium is the temperature of that system. And if you change the temperature of that system, it is going to change its equilibrium position, or it's going to affect its equilibrium. So you need to remember, or you need to understand, that some reactions, when they proceed, they actually give off energy. So an example of that would be combustion. Combustion actually gives off a lot of heat. And other reactions, instead of giving off heat, they actually take heat in or absorb heat. An example of that would be melting ice. For an ice cube to melt, it actually has to absorb heat. So because of that reason, heat can be thought of as either product or reactant, depending on, if it's producing, giving off heat, it's a product. Or if it's taking in heat or absorbing heat, then the heat would be a reactant. So we're going to treat heat, we're going to write it into the equation and treat it as if it's a reactant or a product. So you'll be given equations, and you'll see that heat is going to be written into the equation either on the reactant side like it is here, sometimes on the product side. All right, so let's talk about what happens when you know which side the heat is on, or the temperature, and what happens when you change the temperature. So here's an example. How would the equilibrium of this equation or this reaction shift if you increase the temperature of the system? So you need to look at where this heat factor is. Is it a reactant, or is it on the product side? Well, in this case, it's a reactant. So you're going to treat it just like you would if it were any other reactant. So in this case, we are increasing the heat, so that means we're adding heat to this, right? So we're inputting heat. So that means we're basically adding something to the reactant side. So your system's going to want, or is going to respond by trying to get rid of what you just added. So the reaction that uses heat in this system is the forward reaction. So that's going to speed up to use up the added heat, and you would say that this reaction is going to shift to the right. And what is that going to do to the concentrations of everything in this system? Well, the concentration of your water, your gaseous water, would decrease because it's being used up along with this extra heat. Your carbon monoxide and your hydrogen gas concentrations would increase because the forward reaction is speeding up. Notice I left out this carbon solid. I left it out because you can't change the concentration of a solid, so nothing would happen to the carbon. All right, let's do another example of temperature. So in this case, our temperature, our heat, is a product, so it's on the right side of the equation instead of on the left like the other reaction. So the question that I'm asking is how the equilibrium would shift for this reaction if you cooled the system. So when I say cooled the system, I mean you're lowering the temperature. So what we're actually doing is we're moving heat from the system. So hopefully you realize that if you take something away, your system's going to want to replace what you took away. So the system is going to speed the forward reaction up to replace this heat you just removed. And so what's that going to do to the concentrations of all of our substances? Well, they're all gases, so they would all be affected. So since the forward reaction sped up, that means our NH3 concentration would decrease, and our N2 and our H2 concentrations would increase because we're making more of these and less of this. So let's summarize what changes in temperature will do. So you need to remember that heat is a reactant and or a product depending on if the reaction gives off heat or takes in heat. So you treat it just like it's any other reactant or product. So if you increase the temperature of the system, then your system's going to try to remove that extra heat. So it's going to do that by speeding up whatever reaction uses that heat. If you decrease the temperature of the system, your system's going to want to replace it. So replace the heat you're taking away. And it's going to do that by speeding up the reaction that makes heat. All right, so let's talk about changes in pressure or volume of a system. So if you have a system that has gaseous reactants and products, those would be affected by changes in volume or pressure because you can compress gases and you can also expand them. You can't do that with solids, liquids, or aqueous solutions. So you need to remember that whenever you change the pressure or the volume of the reaction flask, that the only things that will be affected are the things that are in the gaseous state. You also need to know or remember, because you know this, that an increase in pressure is the same as saying you're decreasing the volume. Because if you increase the pressure of the solution, you're really just compressing that into a smaller space. That would be decreasing the volume. And of course, vice versa. If you decrease the pressure, that means you're increasing the volume or the amount of space that these gas molecules have to roam around in. So here we have this reaction, and this reaction is all gaseous molecules. Just know that it doesn't have to be all gaseous. It just means that only the gases are the ones that are going to be affected. And I want to know how the system would respond if the volume of the container is decreased. So when I say I'm decreasing the volume, what I really mean is I'm increasing the pressure. Right? I'm compressing this gas. So we need to look at what we've got here. On the left side, we have 1 mole of gas. And on the right side, we have 2 moles of gas. So if we were to compress this system into a smaller space, it's going to want to shift in the direction that would have the least amount of molecules floating around, or at least molecules of gas floating around in that smaller space. Because it's a smaller space, it's tighter, and therefore it wants to combine to produce the least amount of gas possible. So if we were to decrease the volume of this container, our reaction, our reverse reaction, would speed up to produce more N2O4 because 1 mole of gas occupies less space than 2 moles of gas. So in this case, we would get an equilibrium shift to the left. So how would the system respond if we increase the volume? So if we increase the volume, remember, that means that we're decreasing the pressure. So we're actually making this a larger space for these molecules to move around in. So it's going to want to shift to the side with more moles of gas because there's more space so that it can. So let's summarize how we would treat changes in gas or in pressure of a system. So if the pressure of the system is increased, which is the same as a volume decrease, the system is going to respond by shifting to the side of the reaction with less moles of gas. So it's going to want to produce less moles of gas because you have a smaller space. So the reaction would speed up in whatever direction would produce less moles of gas. If the pressure of the system is decreased, which means you're increasing the volume, the system responds by shifting to the side that creates more moles of gas because you've provided more space. So it's going to speed up the reaction that produces more gas. All right, so that's all the information, and here's a practice problem. So read the question, pause the video, read the question, answer the questions, and then see if you did them correctly by unpausing. All right, let's see if you got the same answers that I did. So if we were to increase the concentration of HI, we're adding a product. So our system's going to respond by speeding up the reverse reaction to get rid of the added product. So that means that everything on this side, assuming it's not a pure solid or liquid, is going to increase. So our reaction would shift left, our temperature would increase, our hydrogen gas concentration would increase, but our I2 would be unaffected because it's a solid and you can't change the concentration of a solid. If you decrease the temperature of this system, what you're really doing is you're removing heat. So it's going to want to replace that heat by speeding up the reverse reaction. So our H2 concentration would increase. Of course, our I2, nothing would happen to it because it's a solid and you can't change its concentration. And our HI would decrease. If you decrease the pressure, what you're really doing is you're increasing the volume of this solution. So you're uncompressing it, or rather this reaction. So it's going to shift to the right. Now, why is it going to shift to the right? Because there are 2 moles of gas on the right side and only 1 mole of gas on the left. Because you're giving it more space, it's going to want to shift to the side with more moles. So you're going to get a shift to the right. Our H2 would decrease. Our I2, of course, would remain unaffected. Our temperature would actually decrease because we're speeding up that reverse reaction. And our HI concentration would increase. So what if we added some more I2 to the system? Well, since it's a solid and adding more of it wouldn't change its concentration, you would see no change in the equilibrium of this system.